Okay, we'll get started with the second phase of our two-stage to orbit aircraft. This aircraft is going to be dropped from underneath the aircraft that you saw before and fire its own propulsion system and go into low Earth orbit to deliver a mini satellite. So this is the Genesis team.
Good morning. My name is Nick Langenegger. I'm the design team lead for Genesis. Our group consists of myself, Michael Rosnick, Veronica McGowan, Brandon Parrish, Chris Crawford, Morgan Sherry, and Eric Lopez. Now this capstone project spanned 2 semesters. The first semester was AE420, the preliminary design. In this semester, we selected a project, received an RFP, went through conceptual design, followed by preliminary design, where we predicted performance values of the aircraft. This leads into detail design. This current semester, we started off designing a wind tunnel model with recording wind tunnel tests. Those tests were then approved. We fabricated the model, ran the wind tunnel tests. These tests served to either validate or disprove our theoretical predictions. After that, we decided to recommend some design changes. Some of those were approved. We implemented those, retested, and this presentation will end with conclusions and recommendations. So our vehicle is an ambassador. It is the second stage in a 2-stage orbit launch platform. It serves the purpose to take satellites to low Earth orbit. And this is relevant to today's industry as it is predicted that over the next decade, specifically the small satellite industry will be at a maximum. And those companies need a reliable, reusable, and therefore cost-effective method to take their payloads to low Earth orbit. You just heard Launch Tech present their PT-1 design. It is the first stage. It carries us up to 60,000 feet, Mach 0.75, where we detach. So moving into the RFP given to us, it is a combination from NASA and the DoD. 2 of the most constraining factors of this RFP were the 75,000-pound second stage weight limit imposed, as well as the fact that we had to be reusable. These 2 parameters significantly drove our design. Here's a diagram depicting the mission profile. The solid black line depicts us attached to the PT-1 up to our state of separation, denoted by the asterisk, at 60,000 feet, Mach 1.75. We then go up to low Earth orbit, deploy our payload, fire re-enter, and land on a standard 10,000-foot runway. Now, our conceptual design ended with these general conclusions. We decided to go with 2 RL-60s for our propulsion methods. We decided to go with unmanned operation. Furthermore, we went with a delta wing VTOL configuration, as is consistent with the majority of similar lifting body vehicles. And here's a 3-view of our preliminary aircraft design. We ended preliminary design with a cost estimate for the entire project. These were based off of theoretical approximations, equations, and so forth. For an entire 3-system, that's 6-vehicle purchase, an initial investment of $13.5 billion. Each launch would then cost the operator $1.8 million. Now I'd like to introduce Michael Rosnick to go over the preliminary predicted performance values with you.
Thank you, Nick. So, as Nick just stated, I'll be going over the values that were predicted during the preliminary design of the Ambassador for its performance. These were all calculated using methods discussed in Raymer, Grant, and Nikolai, and some of the primary performance information is shown up on the screen. The first plot I'll be showing you is the predicted CL alpha plot for the Ambassador. The aircraft was predicted to have a CL max of 1.1, and the wing was predicted to stall around 37 degrees angle of attack. Now, the thrust required plot is shown, and this is plotted with both the gear in the extended and retracted configurations. With the gear extended, the minimum drag point is at about 105 knots true airspeed, and it moves to about 110 knots with the gear retracted. Now, the drag versus true airspeed plot is shown, and this is plotted in increments of 10,000 feet from sea level to 40,000 feet. 40,000 feet is the altitude at which the Ambassador has fully transitioned from its ballistic phase of re-entry into gliding flight. Now the flight envelope is shown on the screen, and this is also shown plotted from sea level to 40,000 feet. The maximum positive load factor for the Ambassador is 4 Gs, maximum negative load factor of -3 Gs. The Q limit for the aircraft, as shown here, is 250 knots, and this is driven by the maximum landing speed. In flight, the Q limit of the aircraft is much greater than this. Now, the trim plot for the Ambassador is shown with the CM alpha curves. The CM alpha curves were plotted by looking at similar lifting body data, and we found out that similar lifting bodies had a CM naught of roughly around 0.1. So this was used as a starting point. One of the conditions we wanted to test is whether the aircraft could trim to the 8-degree angle of attack landing condition. So the incidence of the V-tail was varied until we reached 0 pitching moment coefficient at our 8-degree angle of attack. One important thing to note is that the V-tail is at a 28-degree angle of attack, so this variation in the tail incidence is at 28 degrees above the horizontal plane of the aircraft. Now the same plot is shown for the Ambassador in the loaded configuration. This is with the satellite payload stowed in the nose bay. The slope becomes more negative, indicating that the aircraft becomes more stable in pitch with the payload loaded. Now we have the roll stability plot for the Ambassador. One thing to note is the slope of this was predicted to be negative, indicating that the Ambassador was going to be stable in roll. Now the yaw stability plot for the aircraft is shown with a positive slope, indicating it was also predicted to be stable. One other thing we wanted to do is we wanted to try the aircraft as a flight test model. You can see that flight test model right here. One of the things we noticed is the design equations we used couldn't account for the lifting body design of our vehicle very well, so we wanted to be able to verify that this design would actually fly. So this model was brought up on top of a larger remote-controlled aircraft and released from an altitude of about 200 feet. The initial tests found out that the aircraft was very unstable in roll. This was corrected by adding a simple RC rate gyro to the aileron channel, and several successful approach and landing tests were conducted, and the vehicle was found to have very good flare characteristics. I'd now like to invite Veronica McGowan to talk about the initial wind tunnel model design.
Thank you, Michael. So everything you guys have heard in the presentation up until this point has been part of the preliminary design portion of the course. Everything from this point forward in the presentation will be part of our detailed design course, or things that we worked on this semester specifically. So the first thing we did this semester was design and build a wind tunnel model to verify these predictions that Michael just discussed with you from preliminary design. So we also wanted to identify some areas in need of improvement so that way we could further perfect the design and overall have a better vehicle at the end of the course. So we chose a 132 scale model. You can see an isometric view of the CAD design there on the screen, and you can also see the wind tunnel model here on the table. We chose the 132 scale model because we wanted to have the vehicle large enough to get good results. However, we did have some constraining factors. These are the same constraining factors you guys heard Launch Tech present as well. Was one of the big ones being not overloading the balance within the wind tunnel. We also wanted to avoid any wall effects, solid blockage. Also, we wanted to keep the cost down. That's a big thing as well, and make sure our model was structurally sound. So the model is made up of 3 different materials. We have ABS plastic, which is printed from the 3D printers or rapid prototyping lab here on campus. We also had steel and aluminum components, and you can see the component breakdown per each material here on the screen. So here's an exploded view of our model. So you can see all the pieces pointed out right now are the plastic parts that we printed from the 3D printer. Overall, it was around $470 for the print. Also, it's one thing to note that the wings and tail surfaces were meant to be removable, so we could test without those. And also the nozzle piece, the most aft portion piece you see there on the screen, that was also designed to be removable, so we could access the inside of the fuselage and adjust set screws and tighten up those removable surfaces. So every project has its roadblocks. We had one in the middle of one of our 160-hour prints. We had a slight offset, about 1/8 of an inch, through the center portion of our fuselage piece. So this was a very big print. It would have taken several hours to reprint it, more than a day, to reprint this piece. And due to the time constraint we had to figure out some way to salvage this piece. So I'll get into a little bit more detail on that in the fabrication portion, but we were able to salvage it and continue with testing. So now it's the same exploded view of the vehicle as you guys saw before, this time pointing out all of the metal components. A lot of these we were able to find as scrap pieces here at our metal shop on campus. What we couldn't find here on campus, we purchased locally at hobby stores, and it was only around $6 for our metal components total. So here's a table with a breakdown of the cost of our vehicle. We're just under $475 for this initial wind tunnel model. So now I'm going to go into the fabrication of each of our components and then overall vehicle assembly. So the first piece we had to fabricate was our Ballast Mount. And so you guys noticed that Launch Tech had one as well. Ours was for the same intention, to lift the model slightly above the balance to try to reduce any drag interference we might get from that. So what we did is we purchased 1/4-inch steel from Prescott Steel here locally. We cut it down to the dimensions shown on the left of the screen. We had a welder weld the two pieces together on campus. We drilled holes on the horizontal piece to match those in the pyramidal balance. And we also have holes in the top portion to fasten it to our fuselage. We then put it up against the belt sander and got rid of those sharp edges to try to make it a little bit more aerodynamic in the wind tunnel. Next, we had to fabricate the spars for both the wing and V-tail. The wing spar was made out of 90 thou aluminum. We found a scrap sheet here on campus, so that was no cost to us. We basically printed out a 1-to-1 scale version of what you're seeing on the top left corner of the screen and bent it by hand until it matched the curvature and then epoxied it into the wing. We also had 2 spars on the V-tail surfaces. We had 1 forward, 1 aft, 0.2-inch and 1/8-inch spars respectively. One stuck out a little bit further as that would be the anchoring point to attach it to our model. Another thing we had to fabricate out of metal was the tail mount. Now this is an interface piece that serves to fasten or anchor our V-tail surfaces to the model. Unfortunately, this was originally meant to be printed from ABS plastic, but unfortunately during one of our test fits, we noticed a crack start to develop. Now this is a very important piece. This is what's holding our V-tail surface to the model, so we wanted to make sure that was functioning properly during testing. So we ended up fabricating this out of solid aluminum. You can see on the screen the only thing left that needed to be done at this point was drill 2 holes for the set screw and anchor the point. So I mentioned that 3D printing error we had earlier. So how we accounted for this was we basically cut the model in half right along that center fuselage offset line. And we had a thick enough surface of the vehicle that we could actually drill through the vehicle's thickness and insert remaining rods we had from the V-tail spars. So we epoxied those rods in on either side of the cut. We also epoxied so we could bond the 2 halves together of that center fuselage. And we also had leftover aluminum plates from our wing spars, so we were able to bolt that on either side of the center mount there, just to ensure that we wouldn't get any kind of bending and the vehicle would not disassemble in the middle of testing. Now we did use countersunk screws because we wanted to make sure the top surface of the fuselage was as flush as possible as not to interfere with the flow during testing. So next we're on to model assembly. So the first thing we did was assemble the fuselage together. We did not plan on disassembling the fuselage at any point, so we used a very strong 24-hour cure epoxy to bond the entire fuselage together. We used the same epoxy in the wing and V-tail surfaces to epoxy the spars in, as those were not meant to be removable from the individual components themselves. After that, we applied Bondo in between all the interface gaps of the fuselage, as well as over those countersunk screw holes that we had drilled. We also applied the Bondo where we had put the spars through the wing, because we just had a slot right on top of the wing and then put Bondo over that. We sanded everything down so we had a nice smooth surface, applied a coat of primer and a coat of black paint, and then we used white tufts so that we could get good flow visualization in the wind tunnel. And so what you guys are seeing on the screen now is the initial wind tunnel model. And now this is a 1/32 scale replica of the preliminary design vehicle that we came up with. We used hardware available to us at the machine shop to assemble the vehicle together. And with this model, we went through our first series of wind tunnel tests. And so the configurations you're seeing on the screen, FWE, which stands for fuselage, wing, and empennage, is our fully assembled vehicle. We also had an FW configuration, which is fuselage and wing only, that has the V-tail removed. And then the F configuration, which is fuselage only with the wings and the V-tail removed. So you guys will see these mentioned throughout the rest of the report, so there's a visualization for you guys to see what it looked like throughout testing. Now the reason we did this is we wanted to test how effective our aerodynamic surfaces were. We also have a lifting body fuselage, so we wanted to see the effect of that as well in the wind tunnel test. So we ran through 2 sweeps with each of these configurations, a full alpha sweep and a full beta sweep. So now I'm going to invite Brandon Parrish up. He's going to discuss the results of these tests with you, as well as some modifications we made to the vehicle as a result of these tests.
Thank you, Veronica. So after we completed our first set of wind tunnel testing, we were looking at our data and we noticed a few anomalies or a few weird things that we didn't expect to see. So what you're looking at here now is a small sample of that data. This is a pitch stability plot comparing our full FWE configuration along with our tail off configuration, or FW. Now, a couple of things we noticed that looked weird with this plot was, one, the magnitudes were absolutely huge. We were getting pitch and moment coefficient magnitudes of upwards of 7, which didn't make sense to us. The second thing we noticed was when we took the tail off, it slightly stabilized us, which the tails are at the back of the vehicle, and that didn't make much physical sense. How could you take the tails off and have that help stabilize you in pitch? So we thought something might be wrong here. We decided to review our procedures and check out the wind tunnel testing equipment. And what we found was that during our setup of the wind tunnel, we actually entered our CG improperly into our data acquisition software. So what happened was our CG that we were testing with was very far aft and above the model, which explained our huge pitching moment coefficients as well as the tail off stabilizing effect. So we attempted to correct this data that we had with statics equations, and that went okay, but we didn't really trust that data because we had to make some assumptions about what our data acquisition software was doing, and we didn't trust those assumptions that we made. So from this point forward, we decided we're not going to look at this data. Any data you see from this point forward is going to be either predicted from our preliminary design semester, or it's going to be data from our second set of wind tunnel tests, which I will get to in a little bit. So for that second set of wind tunnel testing, the first thing we wanted to do was retest our full model, our FWB configuration, to establish a baseline to compare our modifications against. The second thing we wanted to do was test our control authority with our all-moving V-tail surfaces. And the last thing we wanted to do was to add a body flap to our model. This is because most lifting body vehicles have a body flap, and we did not have good equations to account for that in our preliminary design semester, so we wanted to add one during our wind tunnel phase of testing to see what its effect on the control of our vehicle would be. Now, the V-tail incidence, the incidence angle is defined, or is with respect to our dihedral plane. The tails are at a 28-degree dihedral angle. And the model already had that capability built into it because that was something we were planning on adding. The V-tails were friction fit into the model using internal set screws, and all you had to do with the model was just grab and rotate the tails by hand. Now, to facilitate this in the wind tunnel test and speed up our time in the tunnel, we marked off our test points ahead of time, as shown here on the right-hand side of the screen. We had test points of -3, +3, and +6 degrees of incidence, and then we also marked off our neutral incidence so that we could reset the tails later. The body flap required a little bit more modification to the model. On the left-hand side of the screen is a ghost view of our aft of our wind tunnel model's fuselage before we added the body flap, and on the right-hand side of the screen is the little bit of added structure and as well as the body flap that we added. So the first thing we added was 2 aluminum plates internally into the model. We drilled and tapped those along with the body and epoxied those plates into the model so that we could just use screws coming up from the underside of the vehicle so that we did not have to access the inside of the model during wind tunnel testing, again, just to speed things up a little bit. Now for the body flaps themselves, they were fixed. They could not deflect like the V-tails could. So those were just made out of flat plate aluminum, and we had 2 testing points, a 15-degree deflection as well as a 30-degree deflection. And each of those are shown on the left-hand side of the screen there along with their overall dimensions. Now to make those body flaps, we sheared the flat sheet of aluminum into the proper overall dimensions. We bent it into shape using a sheet metal brake. And then on the right-hand side of the screen, you can see a test fit of one of our completed body flaps. Now, to make the body flaps, we just used scrap sheet of aluminum that we found in our machine shop, so that didn't cost us anything. So that keeps the overall cost of our model for wind tunnel testing at about $475. Now this is an overall 3 view of our completed wind tunnel model. It shows the 30-degree body flap deflection on the lower aft end of our vehicle there. One thing to note is that this doesn't change any of our overall dimensions that you saw on the original model, because the body flap, when it is not deflected, doesn't add any additional size to the vehicle. Now this is a comparison against our updated 3 view of the vehicle, again showing the body flap is the only change here. And same thing as the wind tunnel model, the overall dimensions of the vehicle do not change with the body flap. So just to reiterate the wind tunnel test that we are doing in our second set of wind tunnel testing here, we are retesting our FWE configuration. We did an alpha and beta sweep with that model just to establish our baseline for comparison against our prelim semester. Secondly, we varied our VTAIL incidence with -3, +3, and +6 degrees of VTAIL incidence. We did an alpha and beta sweep with each one of those test points. And lastly, we reset the tails back to neutral incidence, and we tested a 15 and 30-degree body flap deflection with just an alpha sweep for each one of those test points. And now I'd like to welcome up Chris Crawford to talk to you about our wind tunnel and some of the data that we got from those tests.
Thank you, Brandon. So as you can see, this is an overview of the wind tunnel we used. We used an AeroLab 87 series closed circuit wind tunnel. The test section of this wind tunnel had a cross section of 35 by 42 inches. Inside the test section was a pyramidal balance. This balance is capable of performing the things you see on the screen here. In addition, the maximum and minimum angle of attack shown, and the sides of the window variations. Also, we imposed a 40-pound load limit on this balance, so we do not overload it. One thing I forgot to mention previously was there was a reference point indicated on the balance. This point is where all the CGs are referenced from. So the data acquisition program required inputs from primarily geometric inputs of the model to non-dimensionalize the aerodynamic parameters that we'll be getting from the balance. A couple of important parameters are the X and Z CG location of the model, and also the X and Z CG location of the vehicle. The X and Z CG location of the vehicle were scaled down to the size of the model. This is the model structural test we performed once the model was in the wind tunnel to ensure that it was capable of withstanding the forces in the wind tunnel. From this, we determined that the angle of attack range that we would test at was 0 to 28 degrees, and the velocity would be 24 meters per second, or about 79 feet per second. So in addition, we did a tear procedure to try to counteract some of the effects that the pyramidal balance might have on the aerodynamic properties of the model. This was just done with the balance at 0 degrees. In addition, the primary methods we used to collect the forces and moments on the model were alpha and beta sweeps. These were conducted, an alpha sweep was conducted to find lift, drag, and pitching moment data. In addition, beta sweeps were conducted to find yaw and roll parameters. So you can see here that the next few plots are going to show tests from our second set of wind tunnel testing, like Brandon stated earlier. So this is a graph of the lift curve slope. As you can see, it matches fairly well, except for at about 12 degrees, you can see there's a deviance in the slope of the sail alpha plot. This is due to the fact that the tails began to stall at this point. You can see this corroborated with the flow that is shown on the plot. The Venn diagram did not change appreciably from the preliminary design phase. So here's the Venn diagram again. The drag we predicted was also significantly lower. The reason for most likely reason for the increase in drag was due to the separation of drag on the fuselage that we couldn't really account for in the preliminary design phase. In addition, this CD naught increase in CD naught shifted our first required plot, the minimum drag point, to the left a little bit, and you can see that in this plot here. And this shifted the overall first required plot up because of the increase in drag. Here, now you can see the the pitching moment that we got from the wind tunnel model, as you can see, there's a significant difference in what we predicted. This is primarily due to the fuselage effects that we couldn't readily estimate in the preliminary design phase. In addition, the rolling moment comparison here, you can see, again, a big difference between the model and the predicted values. One likely solution, or one likely reason for this is the fact that the tail is actually blanketed out during side slip maneuvers. Again, here you can see a yaw moment comparison. Yaw moment is relatively neutral compared to the predicted value. And again, the reason for this is possibly due to the blanketing effect of the fuselage on the opposite detail. Here now the plots after this will show the modifications effect on the stability of the ambassador. As you can see, for the body flap, deflecting, the body flap merely changes the value of the pitching moment, not the slope, not the inherent instability of the lifting body. And in addition, it's also important to note that at higher deflections of the body flap, it becomes less effective. This is the effect of the detail on the pitching moment of the ambassador. You can see, as expected, increasing the incidence of the detail decreases the value of the pitching moment. Again, however, this doesn't change the slope of the scene alpha. One other thing to note is that there's a sharp increase at about 8 degrees in various points. This is due to the shifting stall of the tail as the incidence increases. Also, you see kind of a bottlenecking of the data around the zero and positive incidence angles of the tail. We theorize this is due to the downwash effect that is induced on the tails of the model. Again, this is the effect of the tail incidence on rolls, and as expected, they decrease the value of the rolling moment. You also notice some variance along the slope. One of the theorized reasons for this is due to the effects of the fuselage and the congestion and flow at the tails. This could vary the value that the pitching moment. And also the effect of the details on the yaw is that increasing incidence increases the yaw moment. So here you can see a plot of the body flap effectiveness. You can see that while the body flap does not change the slope of the overall aircraft CN alpha, it does shift value and is effective at doing that. You also notice that the trend is fairly nonlinear, as I indicated earlier. In addition, the detail has similar nonlinear trends. You can see where the data earlier was bottlenecked, where slightly positive angles of attack, or excuse me, incidence angles of the detail is not nearly as effective as if it were a negative deflection. Again, this is theorized to be due to the fact that at negative incidence angles, the detail is removed from some of the congestion present on the upper surface of the ambassador. So from this, we were able to plot more or less a tested control region of our vehicle. Because of its instability, we wanted to figure out where our aircraft could fly at. As you can see, the upper surface was plotted by using the minimum deflection of the incidence in the body flap, and the lower surface is plotted by using the maximum and combining that with the maximum of both control surfaces. An important note is our landing condition at 8 degrees. This is within the tested control region. Now I'd like to welcome up Morgan Cherry to talk about the flow visualization and the requirements.
Thank you, Chris. So as Veronica previously mentioned, we added tufts to the model to visualize the flow. So we to capture the flow visualization, we took pictures from the side of the model and on top of the model at every angle and configuration. Now, flow visualization is important because it can be used to see the flow over the model, and it can serve as a verification for the solid and vortex flow patterns seen in the plotted data. So the first disturbance in the flow we saw was at 8 degrees alpha on the wings. So at the leading edge of the wings, the tufts began to curl outward and around, indicating leading edge vortex flow. Also at 14 degrees, we see that the wings are now dominated by this leading edge vortex flow, with the tufts curling around and pointing along the path of the vortex. Now, also at 12 degrees, on the underside of the tails, we noticed there was disturbed flow. Now, this disturbed flow could be due to forebody vortices. However, because the flow wasn't visualized off of the surface, we could not verify this theory. Also at 12 degrees from the top view of the tails, you can see that we're starting to get some flow separation. So at 12 degrees, the tails are beginning to stall, and by 22 degrees, the tails are fully stalled. Also, as Chris previously mentioned, we were seeing downwash effects on the side of the model from the wings. So to the left of the dash line, you're seeing how the tufts curl upward with the flow. However, to the right of the dash line, the tufts are now parallel to the side of the model, indicating those downwash effects. Now, for a VTOL incidence angle at -3 degrees, we see that the tails are beginning to stall at 14 degrees and are completely stalled by 18 degrees. And then at an incidence angle of +3 degrees, the tails begin to stall even earlier at 8 degrees and are completely stalled by 14 degrees. And at an incidence angle of +6 degrees, the tails begin to stall at 6 degrees and are fully stalled by 10 degrees. Now the pattern we're seeing here is the tails are now fully stalled 4 degrees earlier as the incidence angle is increased. Now we do meet all of the RFP requirements that you're seeing on the screen. However, we barely meet the weight requirement of 75,000 pounds and delivering our satellites to low Earth orbit. So low Earth orbit extends from 87 nautical miles to 174 nautical miles. And the reason we're only reaching 87 nautical miles is due to our weight and the current propulsion systems available to us. Now we also meet the RFP and CFR requirements listed on the screen as well. The only thing left to do would be able to acquire mission and operator licenses. Now I'd like to invite Erica to talk about the structural layout and analysis.
Thank you, Morgan. Now what you're seeing is the VN diagram for our wings. This is not to be confused with our flight envelope. This is in keys, not true airspeed. So since our wings are so small, they produce very minimal lift, the gusts have very minimal effect on our overall structure for our wings. What you're seeing now is our ghost view of our overall internal structure. You can see that top view and underside of that. To further go into our internal structure, you can see it on our screen. What's in purple is the tank braces. It's what's in between each tank to help brace them. The tanks are shown in yellow. Our tanks are indeed structural, since at any point in time throughout our mission, there will be anywhere between 6 and 14 atmospheres at all time. There are torsion braces between each tanks shown in green. They help prevent torsion as well as give us a mounting point to mount our vehicle to PT1. And then there's also a keel beam running along the total bottom side of our vehicle to help prevent bending. And then the wing and tail structures are shown in light blue and red respectively. So the material we chose for the majority of our internal structure is MTM45. The key parameters of this material is shown on screen. These parameters were used for our ANSYS analysis we did on our wing and tail structures. To further go into the layup of our wing structure, you can see it shown on the screen, and some of the key parameters pulled. The main and aft spar were a 28-ply layup. The skin was a 6-ply layup, and the ribs were all 12-ply layup, and you can see the thicknesses respectively there in the table. So what's shown on the screen is a picture pulled from ANSYS Workbench of the wing internal structure. This is shown as the maximum shear stress shown there. Now to go into further detail of our tail structure layout, one of the biggest things is the pivot tubes. Since our V-tails are all moving, this is the point at which the V-tails are solely attached to our vehicle and pivot a point. That, along with the forward spar and aft spar, are all 28-ply layup. The skin is once again 6-ply, and the ribs are once again 12-ply, and you can see the respective thicknesses there in the table. Once again, what you're shown is the picture from ANSYS Workbench of the internal structure of our V-tails. Once again, this is shown as the maximum shear stress. Now to look at some of the key values pulled from the overall ANSYS analysis. Some of the big one is the principal stresses, as you can see highlighted in yellow. The maximum stresses, both from the analysis, were about 20% of the overall maximum compressive and tensile strength of our material, so it holds up pretty well. One of the biggest things is the deformation of our V-tails. It has about over a 9-inch deformation at the tip of our vertical tail, so it's something to look into for the research of our structural layout. And now I'd like to invite Nick to talk about the labor cost account.
Thank you, Eric. So here, as you saw with launch deck, is the hours weekly that the group has logged. You can see our predicted hours in blue there, and the red line follows that fairly closely. Moving into the breakdown of hours, there was 5 different categories listed in the table. We logged these hours in categories each week. Note that the blue region is product and personal development. This was certainly a research project, as there was no courses at Embry-Riddle readily available to teach us about lifting body theory or reentry, aerodynamics, so we did have to do quite a bit of research. And here is a visual breakdown of the cost. Each one of those categories had a dollar per hour amount associated with them. Moving into some conclusions, we conclude that the control surfaces, the V-tail, and the body flap were effective in addressing some of our pitch issues. All it did was give us a region at any given angle of attack where we could manipulate that pitching moment. To be specific, that didn't affect our stability. We are still unstable. Our CM alpha is still positive. Moving into the second, we only analyzed a certain amount of tests. We only did 3 tests for the V-tails, for example, 2 tests for body flap. So in order to expand this control envelope, we would need to do further tests, and that might indicate we need to make the control surfaces more effective. And also, as Morgan stated, we satisfied all the RFP requirements. Which leads into recommendations. First and foremost, we were only able, with our tools, to either predict and test conditions at subsonic speeds, low altitudes. So we didn't have the tools to predict any sort of reentry aerodynamics, nor did we have the capability to predict or test any sort of supersonic characteristics. And when this vehicle does go supersonic, that aerodynamic center will shift and possibly could make us stable. However, we can't speculate on that as we don't have any analysis to back that up. And we would like to increase the camber. Currently, the V-tails are symmetric. We'd like to give them some camber in order to increase their effectiveness. For example, zero angle of attack, it would lower our pitching moment. And finally, we did see some vortex flow with the tufts. However, as Morgan stated, we didn't see, or we couldn't speculate as to where those vortices were going, their path, as we didn't do any flow that is off of the surface. However, if the conclusion that the 4-body vortices were impinging on the tail is correct, we would want to move those flight surfaces in order to potentially negate or at least lessen that impact. So we would move the V-tail up and move the wing aft. With that, are there any questions?
All right, first of all, good job. Felt like you guys did an extremely good job of presenting across the board. So let's go with structures. That's what I'm good at, so I'll stick to that area. So we'll see what you have to say. Overall, it looks pretty good. Could you pull up slide 93?
Just give me moments thinking.
No problem. Take it down. School out time,
When the computer starts speaking, you're in trouble.
All right. So first question, how did you guys determine the rib and spar layout that you guys have there?
Well, this was pulled mainly off pulling an example of what the shuttle structural layout for their wings design was, because they had a similar kind of layout as a truss system. So that's
Okay.
kind of the ideas we came from.
Okay, good job on that. That's definitely a good starting point. A question I have though, in industry, we spend probably 80%, 90% of analysis on joints. Do you see a lot of joints?
Yes, very much so.
Do you see a lot of complicated joints?
Yes,
Okay.
indeed.
So did you, it's kind of difficult because I don't think any classes here go into much of joints. Was that a consideration at all in some of the layout in terms of, I mean, looking at what other people do is great, but then kind of, hey, maybe this doesn't quite make sense there. Any approach like that taken?
Yeah, well, it was very difficult. This is very unique. We had a very small time frame, and in order to do our structural analysis, our structure is very unique. Like I said, we didn't have the tools already, so I had to teach myself how to use Workbench with assistance from Professor Hubman, and that was how we did it, and it was very time constraining, and so they couldn't really go into big details of looking at those joints as well.
Okay, yeah. I think it's overall a pretty good layout. There's only a couple spots, so I just wanted to kind of bring that up as to an area to consider in the future as well. So on slide 95, which is the tail structure, the only question I have, it should be an easy one. So why does the peak stress appear where it is? It looks to me like it's on the front spar about halfway out.
Yeah, because that's right where the pivot tube is right there. So a lot of the forces, because it's more structural where that pivot tube is, because it adds more resistance to bending, and so that's where a lot of the force on the tip is pushing onto that.
That's correct. Good job. So with that, the question is, you guys, I think it was 9 inches of deflection there?
Correct.
Yeah. So how do you plan to stiffen that up to reduce deflection?
Potentially adding another spar through the middle could help prevent some of that resistance to bending.
Perfect. That's right. That's the only questions I had. So really good job.
Thank you.
I echo the same thing. You guys did a good job. Very well. Very nice presentation. I want to start with just kind of commenting on the model construction for the tunnel model itself. You guys did some really nice things with that in terms of identifying how to be able to change your control surface incidence deflections and do things with like the body flap. Those are very representative of how you would do it for real. The friction set on the vertical tail incidence, however, is not. You would more than likely have fixed brackets that you'll take the tail off, you'll screw your incidence on so that you actually know you can maintain that deflection. But the fact that you guys were able to come up with something like that was impressive. I appreciate that. Noticing that those tail mounts were going to crack was also a big deal. That's kind of a segue into the discussion about doing a model structural test in the tunnel. That would never be allowed. The wind tunnels out there that you would use for something like this will actually make you do a full stress analysis on the model itself before they'll even let you in the tunnel. Because if you launch parts down their tunnel and destroy fan blades, they don't appreciate that. I've had more than once we've launched SLA ice shapes down there. I've been picking them out of wooden fan blades for a while. They don't like that. So good job on those. I appreciate that. I would urge you to express caution when you say that you've met all of your RFP requirements. You acknowledge a pitch instability, which means you have an unflyable vehicle that needs to be addressed. You don't meet your RFP requirements. That, in fact, you have to address the re-entry aerodynamics, really any manner. Just be careful of your claims, because you're not there. Remind me of the changes that you made from the flight test vehicle to the wind tunnel. Did you make any physically?
Physically?
Yeah.
No, that model you see there is the black model is the same. Oh, the flight test model. Sorry, I'm going to turn that over to Michael. I thought you were talking about the tunnel.
No.
So from the flight test model, the flight test model was made approximately halfway through the preliminary design of the vehicle. So at that phase, we were looking at reaching a higher orbital altitude. We had a longer fuselage with more fuel in it, and that was shortened a little bit to save weight in the final
okay? You didn't notice any significant pitch instabilities while flying that one.
No, but the model is also flown with a more forward CG, as most remote control airplanes are, just to keep it controllable by a human operator.
Okay, that you have multiple data points. You have one vehicle that you flew, it's a little bit different shape, but it worked. You have one that you tested that doesn't. So this is maybe one of the dangerous areas where you have two data points that say very different things. Now which one do I trust and how do I actually make it work? That's something you just need to consider, but you have something that kind of gives you some guidance. You flew with a more forward CG, okay? Do you need to adjust your limits on the tunnel or do something of the nature? Just something like that. Good job, guys.
Yeah, great presentation. I like the way you all handed off to each other and introduced each other. To reiterate your names again, that was great for us watching you present. I thought you made some really good choices with the flight test model. That's a great way to start out, and you learned so much. Even if that had been a complete and total failure, you would have learned a lot by flight testing that model. And to AJ's point, right, you learned a bunch of stuff up front before you even got to wind tunnel testing, and then when those things disagreed, you could always go fall back on your flight test data because you actually did it. So you're relying less on your analysis and more on what you realized. Concerned about the weight margin, you show that your requirements, you met those requirements. And did you calculate what all those pieces would weigh? Because you came up with exactly the weight that you were required to have.
And it was still estimated, that number was rounded. However, yeah, we are extremely close to that, if not right on that weight limit, if not over it. So what we did in weight and balance in preliminary design was we did calculate all the major systems, their CGs, weights. Didn't get any more detail than that.
It's just that the round number makes me skeptical
Right.
that that is an exact number. And you'll find that in any of the test data that you present, when you have exact numbers and things like that, it raises a question. But otherwise, great job, guys.
Great job. A couple interesting things. Did you test the body flap at 0? So a body flap, or did you assume 0 body flap was no body flap?
Correct, with the latter statement.
Okay. So, and then page 74. You've got 3 points and a very interesting spline. Don't let Excel lead you down the wrong path. That's what that appears to be to me.
There are 4 points.
4 points?
There's one in.
One is 0? Okay. Okay, good. I did not see that marked down. But, so I was concerned that your body flap not being there, not being a tested condition, may affect some of your results. Can you think of any lifting body aircraft that have this type of configuration?
X-37B is one.
37B, is it a full delta wing?
It's complex, yeah.
Yeah, so I think they extended the trailing edge of the wing much further aft, and then they moved the tail up, if I remember correctly.
Exactly, and that was in accordance with one of our...
Yeah, so those, you know, he said he's a structures guy. I'm an old guy, so I go back and look at history because there's lots of good lessons learned out there from it. So that would be, the X-34 would be the other one, and you notice it never flew. So there's another data point that you might want to use. You didn't do anything to analyze gear down? The drag change with putting the gear down.
We did in preliminary design, and when Michael was presenting those initial slides.
Okay, so that your landing analysis is all based on that transition. Okay,
Yes.
good. And then there was comment about 6 atmospheres of tank pressure at landing.
Well, since the tanks, at any point in time, they need to be pressurized to maintain their effectiveness to push fuel out. So they, at any point in time, there would be anywhere from 6 to 14 atmospheres within the tanks, depending on the amount of pressure in it. So we don't know, we don't have an analysis of the exact pressure at which it would be towards the latter because it's all the fuel's gone and it's just the pressure remaining in all the tanks combined, so it would be the lower 6 atmospheres.
So my thought was, is if I was going to be analyzing the landing, I would be using the tank as part of my structure. And so I would need to know the internal pressure. May mean I need to include some sort of inert gas pressurization system, something of that nature. But to me, that would be part of what I would look to for my structure, at least for the fuselage structure.
Yes.
And you had a comment about the cost for Raymer. I know Dan. I know Lee Nicolai. I know all these guys. Don't trust any of them.
We might have heard that, yeah.
Yeah. So I actually will use a combination. I'll do at least 3 different methods to come up with something, and then pick apart, because I've done weights where Raymer's been like, 200% different than Nicolai or Roscom. So just to be a warning as you go out, don't trust any of them.
All of these guys remember one of the very first slides I put up, the very first day of their prelim class, and they're laughing back there because they know which slide I'm talking about, because it came from one of the panel members that's up here right now. And he says, well, you use CFD, you get a crappy solution, those are your exact words, and you use empirical methods, you get another crappy solution, you use wind tunnel methods, you get another crappy solution, and then what you do is figure out what is, with all the combination, what is the least crappy solution. And I told you guys about that. That's what design is, and that's why you can't get 5-digit accuracy on design. You just can't do it. Thank you very much.